Hi guys, welcome to my home office. Before we get started with this first lesson, I want to show you a little knick-knack that I just have at my house. You guys have probably heard of fidget cubes, but I have a fidget D12. It has a lot of cool stuff on it. So, I don't know, I just think it's cool. So, there you go. Okay, so we are going to continue in Module 4. So this is going to be Module 4, Investigation 8. And we start this off with a particular problem. So suppose you just graduated and you want to put money into a savings account. So let's say you put $1,000 in a savings account with an APR of 2.3%. That compounds quarterly. Compounds 4 times per year. Now, what we did last week, we know how to set up our compound interest formula with this. So here's our general compound interest formula. And given our specific numbers, we can kind of fill in the blanks here. And we get this guy. So for this particular savings account, this function will tell us how much we have in the account after a certain amount of time. And just to make this easier to look at, we're going to simplify this. And it ends up simplifying to about that. And then we can add these two things together. Okay, so this is what we're working with. Now, we can plug in a certain time t and find out however much we want. So, for example, if we plug in 2 for t, we can see how much money we'll have after 2 years. Which, if we type this in our calculator, we're going to get 1,046 and 94 cents. Something like this. So, this is fine. However, oftentimes we want to have a certain amount of money by a certain amount of time. We want to have a goal for our savings accounts. So let's suppose that we did have a goal, say $3,000. So I'm going to erase this. And then I'm just going to rewrite this thing over here. So if we have a goal of $3,000, we're going to set this thing equal to 3,000. And we're interested in finding out how long it's going to take for us to get this $3,000. So we start working to get t by itself. We can divide by 1,000 on both sides. Over here they cancel. Here this simplifies to 3. So 3 will equal 1.023199 to the t power. Now, we run into a problem here because we don't have the tools to get this t by itself. We can't divide this by this number to do it. It doesn't work that way. So we need something else here. And luckily for us, somebody figured this out. In the 1600s, John Napier did this, and he called it a logarithm. So we'll go into more what that means later, but we have this tool called a logarithm, and we can take the logarithm of both sides and it will undo this exponent, and we have t by itself, which when you figure this out and you actually calculate this, this is about 47.90. So for this particular situation, it's going to take almost 48 years for this account to reach $3,000. That's what this means. That's a long time for this. So this is the kind of the reason why we're doing this, is so we can figure out these t numbers here. So let's look at these more. Just more. So we're going to get rid of all this stuff. So the first thing to know about logarithms is, I guess, how to spell them, but logarithms is they are the inverses of exponentials. So if you remember from Module 3, we talked about inverse functions. Logarithms are the inverse function of exponentials. And the other way, exponentials are the inverses of logarithms. So what this means is that for any exponential function that looks like this, so y equals b to the x, it's an exponential function, we have a corresponding logarithmic function. It's x equals log base b of y. And that's how this is read. Logarithm base b of y. So we can switch between these whenever we want. So if we have something that looks like this, we can freely switch it to look like this. And if we have something that looks like this, we can freely switch it to look like this. And this will really come in handy as we go through and try to solve for x or y in either of these, doing this kind of switch. So let's look at some examples for this that I have prepared for us. So, given the exponential function y equals 3 to the x, the corresponding logarithm function is x equals log base 3 of y. So notice the base of the exponential becomes the base of the logarithm. It's supposed to be that way. So another one. Y equals 7 to the x. Well, the corresponding logarithm function is x equals log base 7 of y. Seems fair enough. So, there doesn't have to be an x and y here. We can also have actual numbers. So, if we have that 121 is 11 squared, the corresponding logarithmic form is 2 equals log base 11 of 121. So the logarithm, it tells you the power that we raise the base to to get the number that's inside the logarithm. So it's a little, you gotta do a little bit of a flipping thing, but if you keep this in mind, you're gonna be okay. So, this is our key thing. Now, there are two logarithms that are so common that they have special notation. There's a special way to write them. So, special logs, special logarithms. So the first one is called the common log. This is log base 10. And this one is really common because we as a society do a lot of things in powers of 10. So this, we abbreviate it as just log of x. And so notice there's no base down here. There's no number down here. When you see this, it's assumed to be log base 10. This is the button that is in your calculator, just log. It's assuming base 10. The other one, so an example for this would be if we're asked to evaluate log of 100, well, this is log base 10 actually. So we think to ourselves, what power do we raise 10 to get to 100? Well, we square it. So log of 100, which is the same as log base 10 of 100, is equal to 2. The other special logarithm is called the natural logarithm. And it's denoted ln of x. Now, this is actually log base e, so that special number e we talked about last week. That's what this is. And again, it gets a special name because it's so common. This comes up all over the place with population growth and interest and so many other things that it gets its own special name. So, an example here, the natural log of 1. So if we wanted to evaluate this, what we do, so this is really log base e of 1, and we have a single logarithm, so we can switch to exponential form. So we want to know what number do we raise e to get 1. I'll make it an x. So what number do we raise e to get to 1? Well, it's actually the same for every number. It's 0. So e to the 0 is 1. That's what this means. So again, the common log, a logarithm without a base, is log base 10. And the natural log, ln of x, is log base e. Again, they get a special name because they're so common. There's nothing wrong with keeping them like this. Nothing at all. So that's it for introducing logarithms. Next time we're going to go more in depth about what logarithms can do. Yeah.